Hi, everyone. Welcome to the chapter 2 of Chemistry 101. In this chapter, we're going to talk about measurements in chemistry. So the content of this chapter is mostly related to our scientific measurement and also in our lab measurements in our labs. And here is the structure of this chapter. Okay, we will talk about the system of the scientific measurements, and we're going to talk about different scales, and then what are significant figures. And some of the topic, in fact, you will complete in your web assignments, especially sig figs, measurements, and scientific notations. And then in the last part of it, we're going to talk about the density of matters. So these are the structures, and you can notice that we're gonna, I moved the item 10 temperature scale to the front. So we're gonna briefly talk about and move on to the rest of it. Okay, I think structurally easier, all right? So let's take a look at the measurements. Okay, what is measurement? Measurement is basically the determination of something or an object or a matter's dimensions, capacity, quantity, or extent of something. So basically measure and determine the amount or capacity, etc. And measurements can be very like a very wide and broad scope, but types of measurement that are related to chemistry or in science in general are the following types, like temperature, length, mass, volume, time. Okay, sometimes we measure the reaction time, and so pressure, such as the pressure of a liquid or pressure of a gas more commonly. So these are the measurements that are, again, related to chemistry lab or scientific labs. Of course, there are other measurements. First, like I said, I moved the temperature to the front. Okay, hope you to get like a very brief introduction about what measurements are, and also most importantly, what do we measure and what are the scales of temperature measurement. I know you guys are familiar with temperature, right? We have temperature, we have a thermometer in our home, in our AC system all the time, but we're actually using a different temperature scale than we use in our scientific labs. As you can see here in this picture, we mainly have three major temperature scales. One scale is called Celsius, another one is called Kelvin, and the third one is called Fahrenheit. The one we're using every day in home here in the United States is actually Fahrenheit. If you notice that the Fahrenheit temperature scale, the water freezing point, of course, is 32 degrees, and the water boiling point is 212 degrees. So between water freezing and water boiling, there are 180 degrees. So this is some general scales about the Fahrenheit. But most importantly, what we will use in our scientific labs, including in your hands-on labs, in your home kit labs, the temperature scales will be on Celsius. And of course, we're going to use Kelvin in our later chapters as well. So basically in scientific labs, Celsius and Kelvin are the units or the scales we describe temperatures. And what's in common about Celsius and Kelvin is between what we just mentioned, between the freezing point of water and the boiling point of water, there are 100 degrees instead of 180 degrees in Fahrenheit. You can see here in Celsius, the water freezing point is 0, the boiling point of water is 100. So between 0 and 100, if you put 100 marks, you get 100 degrees. That's basically how our thermometer is made, manufactured, in fact. So the water freezing point is 0, water boiling point 100, and 100 degrees between freezing and boiling basically is the Celsius scale. And of course, 100 divisions between 0 and 100. And what's different between Celsius and Kelvin is between water freezing and water boiling, there is also 100 degrees for Kelvin, but the 0 point is different between Kelvin and Celsius. For Kelvin, the water freezing point is 270 273. The water boiling point is 373. You can see that between 273 and 370, there's also 100 degrees. So Kelvin and Celsius, their degree amount is actually the same, or in another word, 1 degree in Celsius is the same as 1 degree in Kelvin, but their 0 point is different. For Kelvin, for Kelvin, the 0 is the lowest temperature. We call that absolute zero. Absolute zero. That is the lowest temperature the universe can get. But for Celsius, the 0 is actually minus 273. But again, these two temperature scales are related, but Fahrenheit is a different temperature scale. Okay, again, this is some introduction, but here are some mathematical equations that can convert between these scales. Most importantly, like we said, we will use in our chemistry class and also in our scientific labs are Kelvin and Celsius. So these are the two mostly commonly used conversions between these two temperature scales. Basically, Kelvin equals to Celsius plus 273, or Celsius equals to Kelvin minus 273 degrees. So you can see that difference between Kelvin and Celsius is their 0 point is different by 273. 0 of Kelvin is really 0, but 0 of Celsius is actually already 273 Kelvin. Okay, and this is the conversion. And if you're interested, this is the conversion between Fahrenheit and Celsius, and you can do your conversion too if you're not sure what the temperature of for example, room temperature, you're understanding 75 degrees, 78, you can convert it to Celsius and see what the room temperature is in Celsius. But again, in this class, we will use Celsius and in Kelvin. We will not use Fahrenheit. Okay, next, like I said, we briefly talk about temperature. Let's officially get into the systems of measurement. Okay, when we talk about the measurement systems, we usually have two types. Okay, one type is called the English system. Okay, English system mostly used in commerce, such as the units of English system is what we are actually familiar with daily, our daily lives, like inch, foot, pound, quart, and gallon. These are the English system units. However, in our scientific literature, in our real science literature, on our chemistry and physics, etc., our books, what we're using is called the metric system, or called international system. Okay, international system. And these systems are used in scientific work, and the units for these systems are no longer inch or foot, but grams, meter, and liter. And what's more important about metric system is they are actually more convenient to use. I know you guys are convenient to use English systems already, but in fact, metric system is more convenient to use because they're decimal unit system. They're by 10. Okay, the one unit versus another, they're by actually 10 units. We call decimal unit system. So we're not by 12, we're by 10. So it's actually more convenient to use metric system. Okay, here's a map showing you that, as a matter of fact, almost the whole world is adopting the metric system. The world, or the countries in the world that are not using the metric system are still using the English system are in gray color. You can see that one of them, of course, is United States. Okay, another two countries is Liberia and also Myanmar. I think that's how I pronounce it. Myanmar, this country. Okay, this is an Asian country. So these are the three countries actually currently are not using the metric system, but all the green colored countries are actually already adopting the metric system. Okay, including Europe. Okay, now metric system units, okay, metric system units, or the measurements for each type of measurement, they all have a base unit for each measurement. Okay, for example, for time, the base unit is second. Okay, for length, the base unit is meter. For mass, the base unit is gram. And for volume, the base unit is liter. You can see that these are the base units for measurements. And someone want to ask, what if the measurement we got is too big or too small for using a base unit? Don't worry. Okay, we have a solution to that. We use prefixes to be added to the base unit to indicate the size of the unit. Okay, for example, a lot of you have heard if we add K in front of gram, we would get kilogram. right? Kilogram stands for what? K stands for 1,000. So a kilogram basically means 1,000 grams. So with that prefix, we can change the gram unit to a larger one, which is what? 1,000 grams. We call that a kilogram. But again, the prefixes are independent of the base unit. So basically, you can use the prefix K in many other units. You can use K in front of gram. You can also use K in front of meter. For example, we can convert a meter to what? 2 kilometers. So this is commonly what we're using for metric systems units. We're having a base unit for each measurement, and we also use these prefixes to indicate the size of each unit. Okay, here this table shows you the commonly used prefixes. You can see, or we can saw that called multipliers or fractional parts, but they are basically the prefixes for basic units. Okay, here the capital G, you can see the largest one, stands for a billion. The capital M stands for a million. K stands for 1,000, lowercase k. D stands for, again, K, capital M, capital G, they're actually bigger. They're actually making the basic unit bigger. You can think 1,000, a million, and a billion. But after that, the D, the C, and M, they're going to make the unit smaller. So they're called fractional parts. Okay, for example, D, we pronounce deci, is 1/10. Okay, 1/10. So for example, if you have a decimeter, okay, dm, that means what? 1/10 of a meter. The same, if I have a C, okay, centi means 1/100th of something. For example, cm, centimeter, means what? 1/100th of a meter. So 0.01 meter. Okay, and following on is m, lowercase m is milli, stands for 1,000th. Okay, and mu, okay, Greek letter pronounced mu, stands for micro. We pronounce micro, stands for 1/1,000,000th. Okay, 10 to the negative 6, and then followed by nano, 10 to the negative 9th, and also pickle, 10 to the negative 12th. So you can see that these are the units that are placed in front of the big units, of the basic units, to change their sizes. For our class, I strongly recommend you, or I should say I require you to know the letter, and also, of course, how do they pronounce, and also the size of each of the prefixes in pink, okay, in pink, including mega, kilo, deci, centi, meter, milli, and micro, okay, because we're going to use these prefixes frequently throughout this class. Okay, for example, the quick concept check asks you, which of the following represents the largest measurement? Okay, among these grams, you can see that these are all grams related. Gram, microgram, nanogram, kilogram. Okay, first basically asking which one of the prefixes is the largest. Among these prefixes, the largest, of course, is the kilogram. The K stands for what? 1,000. Okay, and after that, we study the metric system and also the prefixes. Let's take a look some of the measurements. Okay, the first one is the volume. Okay, the volume. We know the volume, basic units is liter. Okay, liter. And base unit is a liter. How big is 1 liter? You guys have experience in a grocery store. You can buy 1 liter bottle, right? I don't know, 1 liter is that common, but you can definitely find a 1 liter bottle of soda. Mostly it's 2 liter, but you can find a 1 liter, and that's approximately how much liter is. But 1 liter is basically a large unit already, because you can see 1 large bottle has a lot. Most commonly in our labs, we actually use milliliter. So we put an M in front of liter. Remember, if you guys remember, milli stands for what? Milli stands for 1,000th. Okay, 1,000. So means milliliter is basically what? 0.001 liter. Okay, 0.001 liter. Okay, sorry. Let me erase. Okay, 0.001 liter. Okay, that's basically how much 1 milliliter is. But again, because in our labs, most commonly, we don't deal with large amount of liquids. So for most commonly used is actually milliliters by placing a prefix milli in front of liter. Okay, that's for liquid. If we want to use to measure the volume of solid, instead of using liter or milliliter, we use centimeter cubic. Okay, centimeter cubic basically is the dimension cubic. Okay, if our dimension, our length unit is centimeter, then the volume will be a cubic of the length, right? Cubic of the dimension. So it's centimeter cubic. Okay, and also a very useful conversion, 1 centimeter cubic basically equals to 1 milliliters. But these two units, one is for liquid milliliter, another one is for solid centimeter cubic. Okay. Now, when we measure, not only we're going to use the units, we could describe the units, we also need to know how do we record the numbers. Okay, that's one part of the measurement. Measurement comes with two parts. One is the unit, another one, of course, is the numbers. So when we come with the measurement, we need to know with the numbers. When it comes to numbers and measurements, we have to know two types of numbers. Okay, two types of numbers. One type of number is called exact number. Okay, it's an exact number. Those numbers are actually not from measurement. They are from, for example, count. Okay, if we have 5 glass beads, okay, 5 basketballs, those are not from measurements. Those are facts. And because those are facts, we call those numbers exact numbers. And exact numbers come with no uncertainty. Okay, that's one of the most characteristic feature of exact numbers. That's why we need to learn this type versus the other type. Okay, one type, again, exact number is the one with no uncertainty. It means what? It is fact. Okay, there's certain, no uncertainty. Again, for example, 1 minute is 60 seconds. Okay, we know 1 minute is 60 seconds. So that 60 is a fact. There's no uncertainty in it. There is no estimation in it. And those numbers, again, like counting or some 1 minute is 60 seconds or one dozen is 12, for example. These numbers are exact numbers. They have no uncertainty. And another type of number, which again is now from measurement. And those numbers come with uncertainty associated with it. Okay, associated with it. And those numbers are called inexact numbers. Inexact numbers are basically, again, numbers from measurement. When you measure, you always will include some degrees of uncertainty in it. Okay, again, when you measure, you will always include some degrees of uncertainty in it, because we are measuring either using our eyes, our ears, or our hands, and also we're borrowing some instrument. And no matter what we're using, we will include some types of uncertainty, which we'll talk about that in the next few minutes. But again, make sure you know these two types of number when it comes to measurement. One type is exact. They're not from measurement. But if you get a number from measurement, any type of measurement, anytime a measurement is made, those numbers are called inexact numbers. Okay, inexact numbers. And again, inexact numbers or numbers from measurement, they always have some degrees of uncertainty. Okay, uncertainty. So what does it mean, uncertainty? Okay, what does it mean, uncertainty? And we're going to see that right now. For any measured number, okay, for measured number, no matter how long or how short the number is, it normally comes with a few digits of certain and the last digit or one digit that is not certain, or we call that estimate. Okay, because of that last digit that is not certain or that is from estimation, we know the whole number will have some degrees of certainty. Again, when you measure something, you always have something that you are certain, and then you have one digit that is not certain, that is from your estimation. And because of that, you have uncertainty. I know you guys are still confused. What do you mean of some certain, some not certain? Let's take a look. Okay, let's take a look at this map before we go back to the picture. Okay, let's take a look at this picture showing two rulers measuring the same object. Okay, same wood stock or whatever case object. The left ruler, you can see that, okay, if the unit is centimeter, you have 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeters, and etc. But between 3 and 4 or 2 and 3, between each centimeter, there's no small divisions. And that's it. The small division is only 1, 2, 3, and 4. And you can see that if I place this stock okay, against the first ruler, what you see is the ruler. Okay, the ruler can tell this stock is definitely between what? Between 3 and 4. Okay, between 3 and 4. So we know that if I measure the length of this stock, okay, if we measure the length of the stock, I know the length is definitely 3 point something because it's between 3 and 4. So the 3 here, because we know it's definitely is bigger than 3, it's lower than 4. So the 3 here is what? It's certain. Okay, it's certain. Again, because the length is between 3 and 4. The digit 3 here is certain because we see that, we know that fact, but it is not 4 yet. So how far between 3 and 4? It comes to our what? Estimation now, because we don't know. Okay, we don't know. We only can mentally divide the distance between 3 and 4 by 10. Okay, we can mentally divide the distance here by 10. And then we can estimate the length of the stock is around 0.7. Okay, 0.7. So the 0.7, the last digit 7 here is what? Is estimate. Okay, it's the estimate. So now you can see that our measurement always come with some digit that are certain, and then what? The first digit that is not certain. The same here, 3 is certain, but after 3, we don't know how far it is between 3 and 4. We have to mentally divide that by 10th to estimate 3.7. Okay, 3.7. So that is the length of the wood stock using the first ruler. Okay, 3 is a certain number, 7 is uncertain, is from estimate. Okay, but 3.7 is the reported measurement length. Okay, now the same logic, if you take a look at the ruler on the right, you will find out that the ruler on the right that is different from the ruler on the left, because between each centimeter, there are 10 more smaller divisions. So that means the smallest division on the right, now ruler B, is no longer 1 centimeter, but 0.1 centimeter, because each centimeter is divided by 10th already. So the smallest division is 1/10 of a centimeter. So now if you look at the length of the stock, you will find out that the length is falling in between 3.8 and 3.7. Okay, 3.7 and 3.8. So now we know that for certain it is 3.7 something because it is between 3.7 and 3.8. So we know 3.7 now is what is certain. Okay, this part is now certain. And if this part is certain, how far it's between 3.7 and 3.8, now it comes to our estimate again. Okay, we need to mentally divide that 1/10 into another 10th to estimate, is that half between or lower than half or bigger than half? In this case, is actually lower than half. So we estimate 3.74. And the last digit 4 is now what? Is now estimate. Okay, now estimate. We're estimate only one digit. Okay, only one digit. So now we can see that because different ruler come with different uncertainty, we know that measurement made with ruler A will have greater uncertainty because ruler A you can only estimate to the what? To the 10th, but ruler B you can actually estimate to the 100th. Okay, 100th. So different ruler have different uncertainty. The first one has greater uncertainty, but it tells us here, okay, each measurement, it comes with certain digits and the first uncertain digit. You only need to estimate one number. Okay, only one number. So now a quick question to ask you: if you see some numbers from a balance, okay, these are devices called balance. They're not called scales. Okay, if you see some readings on the balance screen, are these numbers exact number or inexact numbers? Okay, give you 1 second to think about, 3 seconds to think about. Okay, the answer is both of these numbers are inexact numbers, even though we're using some electronic instrument, and they have their estimate as well. So if you look at these readings, the last digit, the 5 here, and also the last digit, the 0 here, are both actually estimated by the machine. Okay, they're also estimated. The first few digits are actually certain. The last one will be estimated. But both numbers are what we call here inexact numbers because they are from what? From measurements. Okay, from measurements. Okay, here is a quick exercise for you. Okay, if you can, when you're studying, you can actually cover the answer. See if you can read the temperature of this thermometer. Okay, you can see that the temperature here is showing you, is this 100? So it is 101, 102, 103, and 104. So the reading here is actually between 103 and 104. Okay, 103 and 104. So we know that 103 will be a certain reading because it is between 103 and 104. But now 103 is certain, but how far is between 103 and 104? We need to mentally divide what that between the 3 and 4 into 10th, and then what? Estimate. And looks like the reading is slowly that lower than half of 03 and 04. So estimate 103.4. So the last digit 4 is what? Is estimate. Okay, is estimate. So again, when you make readings, you need to take a look. What is the smallest division? Okay, what is the smallest division? Then you always have to mentally divide that smallest division into 10th. Here, the smallest division is 1, right? 3 and 4, the smallest division is 1. So you have to mentally divide that 1 into 10th, then estimate to what? To the 1/10. Here, the smallest division is 0.1 because between 3 and 4, there are 10 more divisions. So you have to estimate that 0.1 into another 10th. So you can estimate to 1/100th. Here, the smallest division is 1, 103, 104. So you estimate that smallest division by 10th, you need to estimate to 1/10. So that's why you're estimating 0.4. Okay, 0.4. So always remember when it comes to reading, you have some certain digits and some one digit of uncertain. And again, the uncertain digit is determined by the smallest division. Okay, the smallest division. Okay, now after we study the measurement, we know the numbers from measurements are called inexact numbers. But inexact numbers doesn't mean they're not meaningful. They're actually meaningful. And a meaningful number are numbers including the certain one and an uncertain one from estimate. And we give these digits, okay, we give these digits, including the one that was certainty, known with certainty, plus the one digit that is the one we estimated. We call all those digits significant figures because they're meaningful. They're actually from a valid measurement. And we call those digits significant figures or significant digits. Okay, to be shorted, to short that phrase, significant figures, we're gonna call it a sig figs a lot throughout this chapter and throughout this class. So again, what are sig figs? Sig figs are the digits that include all the certain part plus one number of what? One number of the uncertain part or one number from the estimate. For example, the one we just did, 103.4, including the certain one, 103, and that 4.4. Those 4 digits are called sig figs. So this measurement, this reading, 103.4, has 4 sig figs. Okay, 4 sig figs. Now, some measurement, okay, after we got a measurement, we got a number, including the certain and the one digit from the estimate, we have to know how to count the number of sig figs when you have a measurement, because knowing the number of sig figs will help us to carry out calculations. Because in the end, after we use our numbers from our measurement, we're going to do some calculations to get our final result. And our final result will depend on the number of sig figs from our measurements to actually determine how many sig figs we're going to keep in our final result. So knowing the number of sig figs will be important in our calculations. So here are some rules for determining the number of sig figs once you have a measured number from scientific measurement. Okay, the first rule is in any measurement, all the non-zero digits are significant. Okay, that means you need to count in all the non-zero digits. Means what? 1 through 9. As long as the digit is not 0, then that digit will be counted as significant. So you can see that 3, 4, 5, 6 has 4 sig figs. 1, 2, 3.45 has 5 sig figs because all of the digits are non-zero. Okay, very straightforward. Now, after we know that non-zero digits are significant, so the only thing we need to worry about is what about 0? Okay, when it comes to 0, there are few scenarios. Okay, there are few types of zeros we need to look at, and that is the slightly more confusing part. Okay, the first type of 0 is called the leading 0. Means what? The zeros in front of at the beginning of a number. Okay, like this, 0.048. If that's the case, the zeros are not significant. Or again, leading zeros do not count as sig figs. So 0.048 actually only have 2 sig figs, 4 and 8. Okay, the same 0.00052 has only 2 sig figs because again, this number has all the leading zeros and 2 non-zero digits. Okay, that's the first type of 0, the leading zeros, not significant. The second type of 0 is confined 0 or buried 0. It means 0 between non-zero digits. If that's the case, these zeros are always significant or always counted as significant numbers. So here in this case, 16.07, the 0 is confined between the non-zero digits. That is significant. So this measurement has 4 sig figs. 1607 are all significant. Okay, the last scenario is training zeros. Okay, training zeros. And training zero come with 2 types as well. The first type is if the 0 is to the right. Okay, the 0 is the training 0 and the right end of the number if it is a number contains a decimal point. Okay, it is the number containing a decimal point like these 9.300 or 12.2300. These zeros at the end of the number, if it is a number that contains a decimal point, if that's the case, these zeros are significant. Okay, are significant. So 9.300 has 4 sig figs, 12.2300 has 6 sig figs because they're the zeros at the end of the number and that number has a decimal. If the number does not have a decimal, if number does not have a decimal, then the trading 0 at the end, right end of the number are not significant. For example, 150 with no decimal point only has 2 sig figs. That 0 is not. But 150 point, okay, if you have a decimal, then that point makes the 0 significant. So that 150 point has 3 sig figs. Okay, 3 figs. So again, if you want to write a number without a decimal point, then if you want to indicate the correct number of sig figs later on, we're going to talk about, it is better to use scientific notations instead of using just 150 straightforward. If that's the case, it's actually very ambiguous. It's very hard to tell how many sig figs. Normally, we'll assume that 0 is not significant with if you don't put a decimal. Okay, and we need to avoid using writing a number in that way. Okay, again, leading zeros not significant. Buried or confined zeros significant. Training zeros significant if there is a decimal. There is a decimal. And if it is not, if there is no decimal, we avoid writing numbers like that way. Okay, in that way, we use scientific notations later on. We're going to talk about. Okay, talk about. So after we talk about the number of sig figs, then we're going to carry out scientific notation calculations. Okay, we're going to talk about the rules for calculations right away. But after you get the result, you normally need to keep a few sig figs as required. But your numbers result from your calculator may be a large number, a lot of digits. So the first thing or a simple thing you need to do is to round the digit to the correct number of sig figs. Okay, correct number of sig figs. If this rounding needs you to round, okay, if the rounding needs you to round to 3 sig figs, for example, then you look at the fourth one. If the rounding asks you to round to 2 sig figs, you look at the third one. Okay, look at the third one. And no matter what digit you're looking at, if the digit is 4 or less, you round it off. Okay, you drop it. If the digit is 5 or greater, you round it up. Okay, you add 1 to the next digit. Okay, for example, I'm pretty sure you guys have done this a lot even in your math class. Okay, for example, this digit, if I want 3 sig figs, okay, 3.72, that's 3 sig figs. So I look at the fourth one, which is what? Which is 4. Okay, 4, I round it off. So I don't need to look at anything else. So 3 sig figs will become 3.72. If I only need 2 sig figs, then I look at the third one. The third one is 2, also round off. Okay, I don't need to look at the rest of the digits anymore. So 2 sig figs becomes 3.7. So it depends on how many digits you want to keep. You look at the one right next to it. Okay, very similar. 5.00673. If I want 3 sig figs, 3 figs 5.00. Remember, the zeros after decimals are significant. So I look at the fourth one because I need 3 sig figs. The fourth one is 6, so I round up. 5.00 becomes 5.01, right? And similarly, if I want 4 sig figs, 5.006. If I want 4 sig figs, I look at the fifth one, 7. Okay, fifth one, 7. 7 is greater than 5, so I run it up. So 5.006 becomes 5.007. Okay, 5.07. So this is how you round very simply by looking at the digits next to it. If it is 4 or 5, drop. If it is a 4 or less, drop. Or 5 or greater, add, increase the digits in front of it by 1. Okay, now after that, let's take a look at the calculation rules. Okay, we know how to round our digits, we know how to round our answers. Let's take a look at the rules for calculating using sig figs. Okay, when it comes to rule for calculation, there are 2 different rules. Okay, different rules. One rule applies to multiplication and division, basically times and divide. Okay, times divide. When it comes to these type of calculations, okay, the final answer, okay, the final answer keeps the fewest sig figs, okay, of all the digits. So if you read the whole rule, it will be the number of sig figs in the answer is the same as the number of sig figs in the measurement that contains the fewest sig figs. Okay, the final answer, sig figs, should be the same number of sig figs as the number with the fewest sig figs. So if you look at this practice, this number multiplied by this number, multiplied by that number. Okay, this number, this number, this number, they have 3 numbers multiplied to each other. One number has 3 sig figs, this number has 5 sig figs, this one number has only 2 sig figs. So multiply after you multiply, the final answer, you're going to keep what? 2 sig figs, because one of the number has only 2 sig figs. So the answer is 45, 2 sig figs. Okay, this one is dividing, 4 sig figs, 3 figs dividing. And the final answer, again, keep what? The fewest number of sig figs, which is 3 sig figs. So we have to round 0.9659 to 0.966. Okay, the 9 round up. So 0.95965 go to 0.966. Okay, again, when it comes to multiplication and division, the final answer has the same number of sig figs as the number of sig figs in the measurement that contains the fewest number of sig figs. Okay, now these are for multiplication and divisions, but when it comes to add and subtraction or addition and subtraction, the rule is slightly different. Instead of keeping the fewest number of sig figs, we keep the fewest number of decimal places. Okay, decimal places. This is even more straightforward. You can see that these numbers adding up together. Okay, the number with the fewest decimal is this one. I only have 2 decimals. So the final answer only has 2 decimals. Okay, here this number 2 now subtract each other. Okay, this number has only 1 decimal. The final answer has only 1 decimal. Okay, again, you need to round up and down. But keep in mind, when it comes to addition and subtraction, you keep the fewest number of decimals of the number that has the fewest number of decimals. Okay, this number has 2 decimal, final answer 2 decimal. This number has 1 decimal, final answer 1 decimal point. Okay, final answer number. So, okay, that's the calculation, how to count the number of sig figs and also how to round. Okay, let's do a quick concept check. Okay, a calculator gives an answer of 8.8274. When you multiply that by that, in which of the following is the answer rounded to the correct number of sig figs? Okay, we're multiplying this guy by that guy. So we know what is multiplication. We keep the fewest number of what? Sig figs, not decimal. Keep the fewest number of sig figs. Between these two numbers, this guy only have 3 sig figs. So the final answer should have 3 sig figs. Okay, if I have 3 figs, this is the third of 3 figs. We look at the fourth one. Okay, we look at the 7. The 7, apparently we need to round up. So 8.82 becomes 8.83. That's how we keep 3 sig figs. Again, 4.60 has 3 sig figs. So we keep 3 sig figs for the final answer. When we look at the fourth one, 7, round up. Okay, round up. Now, finally, when it comes to calculation using exact numbers, remember our measurement numbers with sig figs are all what? For measurements. Okay, they are inexact numbers. But when it involves calculation using exact numbers, for example, like counting, okay, you count coins, you count pennies, okay, the number from counted, they are exact numbers. And when you have exact numbers in your calculation, keep in mind, exact numbers do not affect calculations with sig figs. That means when you consider the rules of calculation, you do not consider exact numbers. Okay, you do not consider exact numbers. Okay, for example, 10 pennies with a thickness of 1.42 centimeters. Okay, they ask you to calculate the average of 1 penny. See, all you need is use 1.42 divided by 10 because 10 pennies is this thick. Then divide by penny is the average thickness of 1 penny. But because the 10 is an exact number because it's from counting, so that number does not affect the scientific, the sig fig calculation. So your original measurement is 3 sig figs because 1.42 has 3 figs. Then your final answer, 0.142, is the one you need to keep because it has 3 sig figs. Your measurement has 3 figs, your final answer is 3 figs, 3 sig figs. And the 10 does not affect calculation because 10 is an exact number. Okay, exact number do not affect calculation with sig figs. They're not from measurement. They're not from measurement. And then quickly, like I said, you will have assignment from web assignment. You can watch a video and get a better idea, or some of you are already familiar with this topic already. So we're going to briefly talk about here about scientific notation. Okay, scientific notation is used when we have a large or a huge number, or when we have a small number or a very small number. Okay, if that's the case, we express our numbers in this format. Okay, a times 10 to the exponent of something. Okay, a, this number is called the coefficient. It must be a single non-zero digit to the left of the decimal. And the decimal can be after the decimal, you can have any numbers, but to the left side of decimal must be a non-zero digit. That means between 1 through 9. 1, 2, 3, 4, 6, 7, 8, 9. Okay, must be these 9 numbers, a non-zero digit to the left of the decimal. To the right of the decimal, again, depends on the sig figs. Times 10 to the exponent. Okay, the exponent must be a whole number. Okay, could be 1, could be 2, could be 3, could be a million, could be 1,000, but must be a whole number. Okay, could be a whole number. So that's basically a format of scientific notation. Something point, something times 10 to the something. And also the exponent could be a negative number. Does not have to be a positive number. Okay, but must be a whole number, -5, -6. Okay, now, how do we convert a large or a small number to a scientific notation? What we do is basically move the decimal. Okay, move the decimal. Remember, scientific notation has a number with what? With a non-zero digit to the left of the decimal. So basically, you move the decimal to what? To the right of the first digit. Okay, for example, here, 93 million. What I do is move the decimal over here. Okay, this was the decimal. I moved all the way to what? To the right of the 9, because I want to make sure there's a digit to the left of the decimal. So I moved it to the right of the 9. And I move it to the left. Of course, in this case, I moved it by 7 places. Okay, 93 million, I move it by 7 places. Then the exponent will be +7. So 9.3 times 10 to the 7. Because I move to the left and make the number smaller, I need to compensate it. That's why the number of the exponent will be positive. Okay, because I move to the left to make the number smaller. Again, I need to compensate. Okay, compensate. Now, if I have a small number like a 0.0000037, small number, the same, I need to move the decimal to where? Now this time to the right of that 3. Okay, remember, scientific notation, you need a digit to the left of the decimal. So you need to move the decimal to the right of that 3. Then this time I'm moving the decimal to the right by 6 times. Now, if I move the decimal to the right, I'm making the number what? Bigger. And I need what? I need to shrink number down. So the exponent will be negative. I move the decimal to the right 6 places, then exponent will be 10 to -6. Okay, 10 to -6. Okay, this is basically how do we convert scientific notation, how number to scientific notations. And the same thing, the vice versa, when you become the bad. Again, you have practice in your web assignment. And last thing, keep in mind, when you use scientific notation, keep in mind only the coefficient part. Okay, only not exponent part. Only the coefficient part becomes significant. Okay, becomes significant. So when you change a number to a scientific notation, you need to ask yourself how many sigfigs you want to keep. For example, 300. You can change it to a way showing 3 sigfigs, like 3.00 times 10 to the second, or 3.0 times 10 to the second. You can see that these two numbers are both 300, but one has 3 sigfigs, another one has 4 sigfigs. Okay, 4 sig. I'm sorry, I have 2 sigfigs. So it depends on how you want to keep the number sigfigs. You need to play with the coefficient. The same here in the second example, 0.004890. Okay, think about it, guys. Leading zeros are not significant. So this digit only have 4 sigfigs, 4890. These 4 digits are sigfigs. So this number has 4 sigfigs. When you convert to scientific notation, you need to keep that 4 sigfigs. So 4.890 times 10 to the -3rd. Okay, because I moved the decimal to the right by 3 times. Okay, to the right by 3 times. Now, original number has 4 sigfigs. After you convert it to scientific notation, don't forget the 0, because you need to keep 4 sigfigs as well in the coefficient, because the coefficient counts in sigfigs. Okay, counts in sigfigs. Okay, this is the quick practice. I'll leave it up to you to practice that. Again, you have more practice in the web assignment of chapter 2. Okay, the final part of this chapter, we're going to talk about more about calculations. But this calculation is something very new to you, but will be very useful in our later chapters. We call the calculation conversion factors. Okay, again, this is the calculation we're going to use a lot in the later chapters when we talk about chemistry calculations. So what is conversion factor? Conversion factor is basically a ratio. Basically a ratio. The ratio that relates one unit to another. Okay, a ratio that relates one unit to another. And because the conversion factor relates to units, we will use the conversion factor to what? to convert between units. Okay, convert between units. And chemistry calculation in later chapters, we're going to show that are basically unit conversions. Okay, essentially, they're all unit conversions. So conversion factor, this calculation method, will be very useful in our chemistry calculations. So here we're going to do a brief introduction of conversion factor and show you how does it work. Okay, show us work. And this is the example we're using here. Okay, we know conversion factor relates to 2 units. So I'm giving you 2 units here. 1 minute equals to 60 seconds. We know that they're related. 1 minute is 60 seconds. So because these units are related, I can use these 2 units to create 2 conversion factors. Okay, 1 minute on top, 60 seconds on bottom, or 60 seconds on top, 1 minute at the bottom. Okay, these are both conversion factors. From what? From these 2 related units, 1 minute and 60 seconds. And now you see that if you have a related 2 units, you can always create a 2 conversion factors. And that is why they say here, conversion factors always come in pairs. One number of the pair being the reciprocal of the other, right? 1 minute over 60 seconds, 60 seconds over a minute. Okay, they always come in pairs. But again, later on, you're going to see that we only use one of them. Okay, here is how do we use it. A kitchen timer shows 450 seconds on the screen. They ask you how many minutes does it represent. Again, you guys, I know you probably can do it as even with your high school or middle school math. But here we want to talk about how do we use conversion factor to convert units, because this will be the fundamental method we use in our later chemistry calculations. So please bear with me, even though you know this question seems dumb, bear with me to take a look how conversion factor works. Like I said, the question says 450 seconds and ask us to what? Show minutes. So we know we're going to relate these 2 units, second and minute. And we know between second and minute, we have these 2 conversion factors, 1 minute over 60 seconds, 60 seconds over 1 minute. So what I'm doing here, is using the given unit, 450 second, that's what we're given, multiply by one of the conversion factors. Okay, like I said, we only use one, even the conversion factor come in pairs. The one I choose contains the given unit at the bottom. Why would I choose that one? Because if the given unit at the bottom, the second can cancel with each other. Okay, because I use 450 seconds multiplied by the conversion factor. If the second in the conversion factor is in the bottom, then the given unit, second, are canceled. So if they're canceled, what you get is what? The unit you want, minute. So the math is basically 450 divided by 60. The final unit is what? Is minute. So this is the idea of using conversion factors. You use the given one, multiply a conversion factor. And the conversion factor, the one you choose, will have the given unit at the bottom. Okay, will be the at the bottom. So multiply the given quantity. You can see I put in red. This is basically, again, what you're going to do in the later chapters in chemistry calculations. We call that dimensional analysis. Multiply the given quantity by one or more conversion factors. Okay, later on, we're going to actually do more conversions in such a manner that the unwanted unit, the given unit, are canceled, leaving only the desired unit on top. Of course, you don't cancel numbers, you only cancel units. You still need to perform the mathematical operations indicated by the conversion factor setup. Okay, let's take a more practice. Okay, practice again. Use this practice after you hear the lecture as well. Okay, after as well. A golfer put a golf ball 6.8 feet across the green. Okay, 6 feet. They ask you how many inches does this present represent? Okay, so basically here we're relating what? Feet and foot and inch. And we know between foot and inch, we have a conversion factor. 1 foot is 12 inch. So I create two conversion factors, 1 foot over 12 inch, 12 inch over 1 foot. That is our two conversion factor. Remember, they always come in pairs. And then I use the given unit, 6.8 feet times one of the conversion factors with what? With the feet at the bottom, right? I choose the one on the right, 12 inch over 1 feet. Feet in the bottom, so I can cancel the feet, get what? Get the inch. So the math will be 6.8 times 12 inch. And the final answer, okay, 2 sig figs will be 82 inch. Okay, 6.8 is 2 sig figs, so our final answer is 82 inch. 2 sig figs. Okay, don't forget we're talking about calculations, measurement, then we need to keep the correct number of sig figs. This is the multiplication. Okay, the 0.6 round up. But here you get the idea. Given unit multiplied by a conversion factor, cancel the conversion factor, cancel the given unit, you get the desired unit. Okay, more practice. Okay, more practice. In this practice, you can see how amazing this method is by using multiple conversion factors. Okay, they ask you, an RA sample has a mass of 4.5 pounds. And what is the mass of this sample in grams? So we're converting what? We're converting pounds to grams. Okay, pounds to grams. And we were given these two relations. Okay, remember, we need to create conversion factors. We need what? We need know the units, how the units are related. Okay, how the units are related. In this case, 1 pound, pounds is related to kilograms. In kilograms, we know K is 1,000, the prefix. So 1 kilogram is 1,000 grams. So now you can see that with the help of the kilogram, pounds is related to what? To grams. Of course, you cannot relate directly, you need the kilograms. So here's the setup. Again, guys, you can practice. Okay, using the given unit, 4.5 pounds, first multiply 1 kilo over 2.2 pounds. Okay, 2.2046 pounds. This is the given. First, I create the conversion factor with pounds at the bottom, so I can cancel the pounds. And after that, I multiply the second conversion factor, 1,000 grams over 1 kilograms. Why do that? Because I wanted kilograms to cancel as well. Because the first step, after canceling pounds, I get a kilograms. And then the second step, I multiply another conversion factor to take care of the kilogram to get what? To get grams. Okay, to get grams. So the math would be 4.5 times 1,000 divided by 2.2046. The final unit will be what? Will be the grams. It will be the grams. And we were given 3 sig figs. So in the end, I keep 3 sig figs. 2.04 times 10 to the third. Okay, 10 to the third using scientific notations, 3 sig figs. So this is a perfect calculation showing you using two conversion factors. Again, each conversion factor is from a relation. Okay, kilograms over pounds, pounds on the bottom. Grams over kilograms, kilograms in bottom, because I want to cancel kilograms in the second step. Okay, and this is another question. I have the setup ready, I have the answer ready. I just want you to cover the answer key. Okay, cover the answer key and work on the questions by yourself. Okay, before take a look answer key again, or think about it. If you cannot solve it, take a look answer key and then cover the answer key again. Work on yourself. Okay, you have to master this method. Okay, not only for the purpose of this chapter, but also for working on the calculations in later chapters. Like I said, dimensional analysis using conversion factors is the foundation of our chemistry calculations. Okay, I'll leave this up to you to calculate this question. Okay, calculate this question. All right. Okay. Last piece of chapter 2. Okay, piece of chapter 2, we want to talk about a very unique property of matter. And also by introducing this property, we can also use conversion factor as well, because it's related to conversion factors. Okay, the property here we're talking about is called density. Some of you may have heard of it, some of you not. Or some of you heard of it, don't know what density is. What is so special about density? Okay, density. We all know that Matter has mass and volume. Okay, mass and volume. If more matter, you have more bigger mass, you have bigger volume, right? Because if you have some iron ball, if you increase the amount of iron, your ball gets bigger, your ball gets heavier. So more matter, the quantity of the matter increases, the volume is going to increase, the mass is going to increase. But if you think about it, how about the ratio of mass over volume? If they're both increasing, but the ratio will actually stay the same, and that ratio we call density. Density is basically mass divided by volume, the ratio of mass over volume, and we call that density. And because density is a division between mass over volume, so the unit of density will reflect that. Mass, we know the unit is what? Is gram. Volume, the unit is what? Liter, milliliter, or centimeter cubic, depends on what we're talking about. So you can see that these are the units for densities. If we're talking about solid, the density unit will be grams per centimeter cubic, because the volume for solid is centimeter cubic. If we're talking about liquid, the density will be grams per milliliter. If we're talking about a gas, because gas normally comes with bigger volume, so we use liter for gas. So the density for gas will be grams per what? Per liter. So you can see the unit reflects the definition of density. And like I said, bigger substance comes with bigger mass and bigger volume. But the ratio, the tangent of this, you can see this is the mass versus volume of brass. Okay, bigger volume, you can see that bigger volume comes with bigger mass. Volume increase, mass increase. But the tangent of it means mass over volume. Okay, mass over volume. The ratio actually remains the same. Okay, that's why the line is a straight line. If it is a straight line, means what? The slope of it is the same. What is the slope? Mass over volume is the slope. Okay, the density actually remains the same, no matter how much substance you have. Okay, that's why we study this property. It's called an intensive property. Okay, it doesn't change as the amount of the substance change. 1 gram of brass will have the same density as a huge bowling of or block of brass. It's independent from the amount of the substance. That's how special density is. Okay, this table shows you the density of some selected substances. You can see that some have greater density, some has smaller density, some has very small density, like gases. You can see the gases density is grams per liter, the liquid, the density is grams per mil, the solid density is gram per centimeter cubic. Okay, you can see the gold has very big density. Okay, gold, that's why a small piece of gold can feel heavy, because the density is high. Okay, it's dense. Okay, 19.3 grams per mil per centimeter cubic. Okay, on the other hand, you can see some gasoline, the density is small compared to water or compared to mercury, etc. Okay, like I said, density is not dependent on the amount of substances. So density is dependent on what? The nature of the substance. Each substance has its own density. You see that on the table listed. So that means using density, sometimes you can even identify the substance, or at least tell the substance if it is pure or not. If the density of something you tell, for example, a piece of gold crown, if it is not 19.3, then that piece of gold may not be pure. Okay, because gold, the density will be 19.3, pure gold. Okay, pure gold. So this is the quick practice asking you to calculate density. Very simple. Okay, by the definition of density is the mass of something, 17.8 grams, divided by the volume of something, 2.35 centimeter cubic. Okay, you can see that both the number have 3 sig figs, so your final answer has 3 sig figs. Okay, the final answer is 7.57. and the unit is grams per centimeter cubic. They don't cancel each other. The units keep, okay, but you keep 3 sig figs, and the calculation is basically based on the definition of density: mass over volume, mass divided by volume. Okay. Now this picture shows you a quarter and a styrofoam. They both have the same mass, but you can see their volume is dramatically different. The volume is tiny. The styrofoam is big. The reason is their density is different. Quarter, the density is big, so the same mass got a small volume. Styrofoam, the density is small, so same mass, you get a bigger volume. Okay, bigger volume. Okay, this is another concept check asking you, if you were given a pound of feather and a pound of lead, the density of each will be different because we're talking about different substances. Okay, different substances. Why their density is different? Because their volume will be different, right? 1 pound of feather, you may have a lot. Okay, 1 pound of lead, maybe this piece tiny. So their volume is different with the same mass, mass over volume. If the volume is different, same mass, the density will be what? Density will be different. Mass over volume. Okay, same mass, different volume, your density will be different. Okay, density will be different. Okay, another interesting about density is showing in this experiment. Okay, that is an object that has a higher density than the liquid will sink in the liquid. But an object with a lower density than the liquid will float in the liquid. Okay, for example, you can see this on the left. We have 3 layers of liquid: syrup, water, and oil. Okay, syrup, oil, water. Grape float on syrup, means grape density is what? Smaller than syrup. But grape sink in water means grape density is bigger than water. Similar, this Lego piece float on water means the density is smaller than water, but sink in oil, so Lego density is greater than oil. The same for the cork stopper. And on the right, you can see that the coin actually floats on mercury, telling you what? The density of the coin alloy metal is smaller than mercury. That's why it can float. It won't float in water, it will sink in water, but it will float in mercury. Okay, this is also something interesting. And here this picture shows you the density of the same substance, water and ice. Okay, later on we may brief talk about, but here the picture shows you ice actually floats in water. It tells you what? The density of ice is actually smaller than water. That's why it can float. Okay, that's a very unique property of water. Okay, we don't talk about a lot in this class, but when water freezes, the volume of the water molecule actually expands. Okay, the gap between water molecule gets bigger. And that makes the density of water after it freezes smaller. That's why ice can float. Okay, this is a very unique property of water, actually makes life possible. Okay, think about, imagine when lake and water freezes, the water freezes on top, not from the bottom. So living things can still live in lake in winter, in frozen lake and river. And finally, density, again, is relating what? Relating mass and volume. So we're talking about relating of 2 units. So that means density can also be used as conversion factor. Okay, conversion factor. So here's what shows. If we have a liquid of 49.6 ml, that's the volume. and then tell you the liquid has a density of 0.85 grams per mil. That's the density. They ask you what is the mass. Okay, what is the mass? We know that density, 0.85 grams per mil, means what? Per mil means 1 mil is 0.85 grams, right? That's what per mil means. So 1 mil is 0.85 grams means these two units are now related. 1 mil of that liquid is 0.85 grams of the liquid. So if these two units are related, I can create these two conversion factors. 1 mil over 0.85 grams or 0.85 grams per 1 mil. Then we do the same thing using the given unit, 49.8.6 mil, that's the given, multiplied by one of the conversion factors with the given unit at the bottom, right? The given unit is mil, so I use 0.85 grams per mil. Mil, and canceled. So the math will be 49.6 times 0.85, final unit is gram. The density has 2 sig figs, the volume has 3 sig figs, so final answer has 2 sig figs, 42 grams. Okay, 42 grams. So you can see that unit of density relates to units, grams and volume. So you can use that relation to create two conversion factors for a substance that can convert between grams and volume. This one we're going volume, we can convert to grams. Another one, if we are giving grams, we can convert volume. But again, the idea is the same, using the given unit, multiply a conversion factor with the given unit in the bottom. So you choose the conversion factor with the given unit at the bottom. Okay, that is all for chapter 2. Okay, a lot of info regarding numbers, calculation, measurement, sig figs, deciding how many sig figs, rounding, calculation, and then conversion factors. Okay, hopefully you can summarize the chapter again, do a lot of practice, and I will see you in chapter 3. Bye now.